Okay, so hello everyone. So welcome to our this week Rogers Efficient AI seminar. And today we're very glad to have the Professor Jeff Zhang from the Arizona State University to give us this talk about the architecting AI system. And Professor Zhang is currently assistant professor in the School of Electrical, Computer, and Energy Engineering at Arizona State. Prior to joining ASU, he was a postdoc fellow at Harvard and earned his PhD from the NYU. And his research group focused on the intersection of the deep learning, computer architecture, VSI, and EDA, with a specific emphasis on architecturing energy efficient and fault-tolerant AI and ML systems. And Jeff is a recipient of the IEEE Micro Best Paper Award and the IEEE Top Picks in Test and Reliability. And I know that Jeff has done a lot of works in the acceleration, compiler, and so on. Now let's welcome Jeff to give us this talk.
Yeah, thank you very much, Bo, for the introduction, and thank you very much for introducing me for the seminar. I would like to thank you because you have been always helping me since I was a PhD student. Today, I'm going to happy to share some of the recent works since I joined the ASU that has been done with my wonderful students around the AI hardware and the systems, and we're going to look at from the algorithm to the hardware versus design perspectives. So let's start the talk by looking at some of the significant gaps in the AI computing today. The first gap I want to share is that if we look at the numbers on the worldwide IC or hardware designers versus the worldwide AI software developers, so clearly the number of hardware designers falling short. There is more than 100x gaps here, so which means we really need more of the students or the workforce development in the AI hardware design side. The other gap is lying on the AI processors, right? So this is being well known that traditionally those general purpose processors, CPUs, even GPUs, if we look at their energy efficiency, right, if we compare with today's most advanced ASIC, specifically designed IC for the AI acceleration, the energy efficiency in terms of TOPS per watt is also showing a big gap, more than 100x. So this all motivate a lot of research, a lot of the teaching around the hardware design, especially for machine learning. So let's start today's talk by looking inside AI systems, especially on the vector search. So what is vector search? Vector search is a kind of the search technique that empowering the modern AI systems. So you can say find a vector search in semantic search, where you need to find a conceptually similar content, right? So this is a different than a keyword matching, right? So traditionally, if we do the keyword matching, you kind of search across a database to find the exactly match the words itself. But the vector search, we are doing it in the vector space or embedding space. So we find a semantically similar content. And the vector search has been largely used in recommendation systems to help the user find the most relevant items that maybe it's a book he or she might read, or it might be a furniture like when you are shopping on the Wayfair. Also, vector search has been seen in visual search. Similarly, instead of finding the similar, let's say, text, now you can using the vector search techniques to find similar images, videos, and more recently, because the large language models has been become such a hot topic right now, and we know that retrieval augmented generation, this RAG techniques can enrich in ARM queries with context and domain knowledge, and also vector search can largely, improve the RAG for ARM queries. So in the real world, vector search has been actually adopted in many this AI companies. For example, YouTube video, right? So the YouTube need to actually process more than 500 hours of video uploaded per minute. And Google search, definitely we are familiar with it. It going to process billions of web pages, which need to be indexed every hour because there are new web pages created every hour. And there are a lot of other companies which would all require to process millions of documentations from thousands of users per second. All of these are empowered by vector search. So how does the vector search really work, right? Here I got a picture from Elastic, which kind of show a good conceptual understanding of the vector search workflow. So from the left-hand side, we know that, right? So we're going to have a database, which might coming from the images, or it's documentations, or it's audios. And then when we do the vector search, instead of directly search on the raw data, we're going to first transform those documents into the embedding, where you can use those embedding models that would help you to create those dense vectors, which is a vector representation of those documentations. Okay, and on the right-hand side, this is where the user might send their queries, right? So as a user, when you're shopping online, you're going to type in some keywords for the item you may like to search, right? So that's is your query. And similarly, when the system got your query, it's going to also translate the queries through the embedding models to generate the vector representation of your query. So now the vector search becomes a search over this query vector over the documentation vector, right? And the way you're going to do that, you can do it as simple as think of it as a nearest neighbor. You basically want to find among those documentation vectors, what is the most or what is the top k most nearest neighbor close to the vector query that you want to find, and then it will return you some results, right? So in terms of nearest neighbor search, you can use many traditional similarity search metric, for example, cosine similarity or Euclidean distance calculation, right? So that's the overall idea of the vector search. But the conceptual idea is simple, but the question is how do we really do the search efficiently at the scale, right? So if we are only talking about two documentation or three or 10 documentation, and then you have a query come in, then it's easy, right? You just brute force search over all the candidate, documentation vectors, then you will be find it. But at the scale, at the industry scale, we are talking about thousands of hundreds of documentations, billions of users. So how do we do the search efficiently, right? So traditionally, there are a lot of vector search approaches, right? So what we list here is several, the traditional vector search approaches. So for example, here is a brute force, right? So when doing the brute force, you can guarantee, right, you will find this 100% accuracy. You will find the most, similar vectors from your database, but complexity-wise is high, right? So you need to iterate through all these vector spaces, and also it will incur some high memory usage on large data sets. So when the data set is large, the time complexity would be very high. Or there are some kind of recent, tree-based, those approximate nearest neighbor search algorithm. For example, KD tree, right, or ball tree. So KD tree has been applied largely in point cloud search. So those approaches are very actually good for the low dimension data. However, it turns out that there is a curse of dimensionality, right? So for data set which is larger than, let's say, 20 dimensions, it actually, the performance of those algorithms degrades similar to the linear search, okay? And also there are some hashing approaches that can provide some theoretical guarantee, but also impractically, there are some suboptimal performance on the real world data sets and also high memory overhead. And what's showing here is another kind of approximate nearest neighbor search method, right? So instead, this method says instead of find the exact match or exact nearest neighbor, can we do it approximately? So, and also, can we do it in a graph-based, right? So those graph-based, the ANN has draw some attention because they were able to achieve very high recall rate, but there are still some computation challenges inside those approaches. For example, the memory overhead, and also for doing a graph-based AI, you need to have an index building, phase that is kind of time-consuming. So besides those approximate nearest neighbor search approaches, there is another kind of ANN called hierarchical navigable small words, or HNSW. Actually, this method has been largely applied in today's industry to power those vector search process. So the HSW actually built on top of two concepts. The first concept is called this probabilistic skip list. So the overall idea of this is that instead of doing the search linearly, if you look at the bottom layer, right, that's the traditional way you can, link list all your documents in the linked list. And then when you do search, you just iterate through this linked list. And this probabilistic skip list build a probabilistic data structure on top of this bottom layer. They also build upper layers, and the higher layer you go, it's kind of a more abstraction view of the bottom layers. So whenever you have some items put in the upper layers, it's going to still coming from the whenever you have items in the top layers, it's still going to have a copy in the bottom layers. But when you do this layered-wise probabilistic skip, you kind of can find some shortcuts into the ground truth items that you might search much longer through a linear linked list. For example, what's showing here is if you start from this layer 3 top layer, you can quickly converge to this item, which is, let's say, the nearest neighbor. So this is one idea that has been proposed in terms of this probabilistic skip to accelerate the search process. The other idea, which the recent research has proposed, is called a navigable small word algorithm. So this NSW algorithm actually try to build up on top of the philosophy of the well-known six handshake rule, right? So we know that all people are six or few social connections away from each other. So then when we build on top of this philosophy, right? So we can build like a small word graph to model the words social connection, and then it can be adapted to model the items, the relationship between items, and by building those small word graphs, right? So the idea is like, for each of the node, you can control the number of degrees, and then you can control the depths of the relationship, right? So build on top of these two existing ideas, this comes with this hierarchical navigable small word algorithms, right? So if you look at it here, they're showing a multiple layered navigable small word. So basically, the bottom layer, you can still view it as the NSW, but then it generalizes from the NSW algorithm to multiple layers, similar to this layered abstraction from the probabilistic skip list. Right, so if you look at it here, this is showing like a graph have been built in the HSW way, and when your query come in, you can quickly navigate to the bottom layer, find the nearest neighbor. And just to be clear, this is still approximate nearest neighbor search process. But if you look at it here, you can kind of find out that at the bottom layers is more dense, and then on the upper layers, towards the upper layers is kind of more sparse, so that you can do this layer-wise navigable small word. So what's the benefits of HSW, right? So the concept-wise is simple, but if we look at the record, which kind of a metric for the accuracy versus the latency, and if we compare the hierarchical NSW, HNSW versus other AN or brute force such algorithms, you can clearly say that on this record versus query time space, right? So HSW win in terms of both the record versus the query time is really on the Pareto front. And if we look at the brute force, it's exact, right? But it's very slow. So in the real world, when the query workload is high, it really challenging the practicability of it. And those tree or hashing method, right? So they when in the high dimension data space, it's not showing the good performance. NSW can improve the record but still slow, right? But HSW really win the game. So this is about the HSW algorithm to enable the faster and high accurate search process. And we started to look at this algorithm, and we found some interesting observation in the HSW algorithm itself, right? So if we look at, let's say we do some search using the HSW benchmarked from some existing data set, right? What we really found out is that when the HSW perform the search process, it kind of you still need to start from the top layer and eventually iteratively find the nearest neighbor on the bottom layer. But throughout this process, it's not kind of one shot, right? So you still need to like traverse a lot of nodes, right? And many of those nodes are actually rejected nodes. Rejected nodes means those nodes on the nodes on those paths are not going to be the nearest neighbors. So going to be visited and then will be rejected, right? And then there would be some nodes actually on the critical path, which we call it decision nodes. Those nodes are the ones that would lie on the shortest path. And if you look at this number of nodes being evaluated on the HSW versus their real distance to the query that you have in the system, right? So you find out that actually only 7% of the nodes would impact the final search results. So this is one thing. The second thing is majority 93 of the nodes are non-critical during a specific search, right? So what does that mean? That means this highly skewed node distribution really motivate us to rethink how HSW should be designed or especially being deployed in the real system, right? So should we really, budget the same amount of computation or the memory bandwidth to all the nodes inside your HSW equally, right? If we do that, we might waste a lot of computation and memory on those 93 nodes, which are non-critical during your search decision. So that's why we propose this AQR HSW, which is an enhanced version of the baseline HSW, and we try to accelerating in search via density, via quantization, and also multi-stage ranking. This work has been recently accepted in DAC 2026, and I'm just give you some quick overview of the work. So for our AQR HSW, it still require the baseline build phase, right? So at the build phase, it's much similar to the original HSW, but we add some optimization on top of it, especially when we get the input data set. We're going to first look at the density of the nodes among your data sets. And then once we get the density of the nodes, so some area, some local area, you have a high density cluster, some area you are more sparse, right? So once we estimate the density, we're gonna do some parameter adjustments. So those parameters are related to the HSW baseline algorithm itself, and we incorporated the density estimation into the HSW build phase to adjust the parameter to amortize those density heterogeneous. And then once we have the parameter adjusted based on the density, we're gonna to perform the vector quantization. So instead of building the index on the original row data set, which is let's say FP 32, right? We're gonna to create a 8-bit version, which is a highly compressed version of the original data. And then we're going to store this quantized data vectors. And then we're going to construct the HSW graph for the quantized vectors instead of the row vectors for the baseline phase. And then you would get a kind of this graph index for the database you would have. So by doing this, we can achieve a smaller build time, and that would help us to achieve high QPS and also high recall for the search. So here is a snapshot of the search phase. During the search, we first gonna to, let's say you receive the vector in the floating point 32 format. Because our graph is built on top of the quantized version of the vectors, so we're gonna to do a quantization on your query. And then once you have quantized the version of your search vector, query vector, we're gonna to perform the quantized search over the HSW we built to get the nearest neighbors for this quantized format. But we still do the quantization, so we're going to lose some precision. So we in this phase, we're not going to do a one-shot search just over the quantized vectors. Instead, we're going to do some coarse grain. So we allow, let's say, instead of top 5 candidates, we're going to make a decision. Now we're going to relax that, right? So during the quantized search, because there are some precision loss, so we're going to get, let's say, top 7 candidates out of this quantized search. And once we have this top, let's say, 70 candidates, we're going to do a more fine-grained search over the floating point precision. So all the this quantized vectors in our database going to be dequantized back to the FP32, and then we're going to compare it with the original FP32. So we're going to search the similarity among those back to the FP32 format. And here we're going to yield about half of the candidates over the quantized search. And then within those top 28 candidates, we're going to say, oh, there is a clear boundary, there a clear separation for, let's say, top 5 candidates among those 20 candidates. If there is, we're going to enable the early termination. So we're going to return this top 5 nearest neighbor. And if not, we're going to perform an exact search over this remaining 28 candidates to enable a fine-grained search, such that eventually you will get a more accurate top 5 nearest neighbors. So this is kind of a multi-stage ranking. You see, we search the multi-stage. However, during each stage, the number of queries you deal with is largely different, right? So at the very front end, you're going to deal with a large number of nodes, but we perform the search over the quantized space. So instead of computing the similarity score over 32-bit precision data, now all the computation going to perform it only on the quantized 8-bit precision. This could help you to enable faster computation, also reduce the memory bandwidth limitation, right? And once you got this quantized search face down, we're going to do a more fine-grained high precision search, but now you are dealing with much smaller candidates such that we can reduce the overhead by, if we are looking at the baseline HSW, you're going to do everything compared to the FP32 search. And then there are some early termination would help you to do some, early exit. So here are some more details about our build phase, but we don't are gonna to look into the detail. Is much similar to what we have talked about, and for the search space, for the search phase is also similar. We do the coarse grain quantized search first, and then we do a symmetric refinements on the full precision re-ranking, and then if necessary, we will enable this exact like a search just on a limited number of candidates. So the my idea is during the search, we want to retrieve top K nodes progressively by avoiding expensive FP32 operations unless necessary. So here are some results coming out of our AQR HSW, where here we evaluated our approach on 4 different data sets, and we look at the record versus the QPS, right? So here the red lines on each of the data sets showing AQR HSW's performance. And for comparison, we compared with a baseline HSW. There is no quantization, no re-ranking, just a baseline HSW. And we also compare with another called scalar, which is a baseline 8-bit quantization, which does not do some careful quantization optimization. And also we compare with another existing work we published at a date last year, where they only look at the density of the data. They do the density aware HSW, but here AQR HSW, we look at both density aware quantization and combined with the the multi-stage ranking during the search. So here are some more numbers on the exact query latency distribution if we compare our query distribution versus the baseline query distribution. Clearly, you can see AQR HSW can maintain a very good, let's say 99 percentile, and also the mean latency compared with the baseline. Also, we found that the AQR HSW can benefit from SMD single instruction multiple data optimize the distance computation because the kernel computation inside the HSW, this vector search is performing a lot of the distance calculation, right? And if you have a batched queries, actually, if your core or if your CPU supports the SMD instruction, we can actually, using the SMD to optimize over multiple different queries. And if we do that, we can achieve higher throughput. This is what showing here when we enable the SMD optimization on top of our AQR HSW. If your processors support that, right, so you can benefit more QPS improvement. And here is a more, a full picture of where we are in terms of the AQR HSW performance versus other existing vector search approaches in the literature. So you can see here we are lying on the operator front in terms of QPS versus record by comparing with many other different search algorithms. So this is about algorithm level system optimization for the vector search. Actually, there is another emerging AI algorithms which has been largely deployed in today's automotive industry. For example, nowadays we know that when we are driving a Tesla, they have the self-driving capabilities. It's a full self-driving capability, right? So in general, those autonomous driving perceptions, they're gonna to do a multitask learning, right? So let's say they take in an image from the camera, and then they're going to do some future decoding, right? Once they have this future decoded representation, then they can perform many different downstream tasks. For example, those what are related to autonomous driving is the semantic segmentation, or object detection, or line detection, right? So those are multitask perception models, which have shown very successful performance in the autonomous driving workloads. However, because all these are neural network based deep learning techniques, so this workload would require massive Mac operations in order to perform inference, right? So that's also the reason why today there are a lot of AI accelerators, hardwares, being designed and being deployed into the self-driving cars, right? Roughly, you're going to have a SoC. Similarly, look like you have a CPU core, you have a lot of memories, you have a lot of controllers, and then you have several data paths, right? So it might be systolic array like 2D, P array to largely accelerate those matrix multiplications or linear transformations. However, we are looking at autonomous driving, right? So this autonomous driving workloads, besides the latency requirements, there are more metrics that we should care about when we are talking about autonomous driving, right? So those autonomous driving cars, there are a lot of constraints. They are definitely energy memory constraints, so that you need acceleration solutions, but also they are voltage constrained. They very uniquely, they also have very different temperature grades. So this constraint would really, affect the resilience or reliability of those autonomous driving workloads, which is safety critical. So we need to pay a careful attention to it, right? So there is actually an automotive electronics council. This council called AEC is responsible for the quality standards for ICs that are specifically used in automotive applications, so that they want to ensure the ICs can handle the harsh conditions inside the vehicle, such as extreme temperatures, right? So here, this specific standard that we talked about is called AEC Q100. So here is more detail about the AEC Q100 qualification for automotive grade ICs. Okay, so what is showing here is several different grades and the corresponding operating temperature range, right? So if you're going to claim your automotive grade ICs can achieve grade 3, then you want to make sure you can deal with all the conditions. You will not have any failures or have any reliability issues under this -40 to 85 Celsius range, right? But if you're going to claim, oh, my IC is going to meet grade 0, then you need to look at up to 150 degrees of temperature testing, right? So this makes the automotive ICs very different than consumer ICs, let's say our mobile phone, right? If you look at the temperature range, it's very different, right? The operating life would be also different. So that really motivate one of the work our group has been doing is that for those multitask perception workloads, and especially if they're going to being deployed on AI accelerators, how would it look like, right? If let's say temperature has a lot of variation, can those ICs be safely, deployed in the real use case? And if so, what kind of grade they can meet, right? So in order to understand this temperature impact, we start by looking at transistor level temperature characterization, and we perform the H-SPI simulation on the ASP7 PDK, right? So we put an NMOS, and we did the output characteristic, we did the transfer characteristic over different temperatures. You see here, there's a grade 0, this is grade 1, this is grade 0, right? So we profiled up to the 150 Celsius degree. And we can see that the transistor behavior, when the temperature goes high, you're going to get a smaller ion, right? So your circuits are going to switch slower, propagation delay would be longer. And also, if you look at the transfer characteristics, at the high temperature, right? So you have a much, much slower turn off, which would lead to higher leakage as well. So all these are not good. And at the circuit level, if we look at a simple ring oscillator, let's say at a room temperature 25 Celsius degree, we build a ring oscillator to be able to operate at 1,000 picoseconds clock frequency. And if we now profile at different temperatures, you would say this delay of the ring oscillator largely increased when your temperature increase. So what does that mean, right? So let's say we don't care about all this temperature variation on our ICs. We just design the AI accelerator at room temperature, and it meet the timing. Let's say this 1,000 is your timing target, and you are happy. And if we deploy that chip in the autonomous driving systems, and if the environment condition cause, let's say the temperature shoot up to 100 Celsius, right? Let's say 125, grade 0. Then what would happen? Your delay would be significantly increased. And if you don't know, if you are not aware of that, then probably it will introduce a set of a violation, and you would see a lot of timing errors, right? And on the circuit level, if you have the timing errors, that would be represented as let's say delay faults. So basically a bit flipped on that path where you have a timing error. So if we have the delay faults going to be shown up at the high temperature, would that become the roadblock for us to achieve the AEC Q100 grade, either 0 or 1? So that's the key question we want to understand in this study. And to answer these questions, we develop a framework that can help us to do the end-to-end delay faults modeling and the mitigation when we are looking at this multitask perception pipeline, and which going to be accelerated by AI hardwares. And this work is also a recent DAC 2026 publication. So at the high level, this framework can do the circuit default fault characterization, and it will also be able to do the fast, realistic cross-layer fault injection. And then we can also use DFA drive to to evaluate the fault while workload mapping, so that we can look at the impact of the delay faults on the multitask driving pipeline. So here are some more closer look at each component of our framework. At the core of the DFA drive, we have a hardware design, a module, which is similar to the traditional, this AI hardware development phase, right? So we have implemented synthesizable systolic arrays, and the framework can automatically extract the text vectors from the workload itself. It will perform quantization, tiling, mapping, scheduling to the systolic arrays. So there's some kind of common methodology. And besides that, because we want to categorize if there is faults or not under different temperatures, so that would require us to have a module that can do fast, not fast, but cycle-accurate netlist level simulation, because those delay impact on the hardwares, you need to simulate it on the circuit level, right? If you only do the RTL simulation, there is no timing delay information being annotated in your simulation. So instead, we need to move to the netlist level, do the delay annotated cycle-accurate simulation, which is very, very slow. But by doing this, we were able to collecting some ground truth data. For example, for each max, we can log its inputs, outputs during this delay characterization. And also, we can also identify, once we know the impact of the delay of each MAC operation at different temperatures, we can tell by comparing to our nominal clock frequency, we can tell if there is a fault or not. And then once we have this infrastructure, which allow us to do a very detailed cycle-accurate level simulation and by collecting a lot of ground truth data, we were able to also build a relatively fast software-based emulation. And here, actually, what we just discussed about the HSW, this vector search, have been incorporated into the fault prediction. So once we get a lot of ground truth data, we can build a graph database to index all the ground truth, let's say, delay vectors, right? And now we can use this graph index to do fast software-based emulation at the software level. Once you have a new max computation data come in, we can quickly retrieve the most similar vector in our database, and then to predict if this current Mac would have a fault or not without running the costly circuit level simulation. So here are some results we were able to show. First thing is about the HSW accuracy, right? Because we do the prediction-based software emulation. If you look at here, these are the different tasks, right? Driving area, line detection, and then detection, right? So here are some extracted layers. If you look at the actual probability of error, which are purple lines, versus our HSW index predicted probabilities, which are very close to the ground truth. And also at the task accuracy level, right? So you can say the blue line are the real full hardware simulation. So those serve the ground truth. And then if we do the software, HSW-based software emulation, we were able to also predict relative accurate results. So by using the DFA drive that we developed, we were able to quickly profile the error rates across different layers for different tasks, right? So what I'm showing here is for different three tasks. How does the error rates per layer of the deep learning model, those specific tasks has been used under different temperatures, right? What you clearly say is there is a lot of heterogeneity in terms of error rate if we're looking at a different task, if we're looking at different layers. Besides the error rates across different layers, we also found a very interesting behavior is that if you're going to use a different systolic array size, let's say you have a systolic array with a relatively large size, 256 cross 256 data paths, or you have a small systolic arrays, which are very small, 8 cross 8, right? How does that, how would that look different? So if you look at it here, right, what we can say to be very consistent across different workloads is that smaller systolic arrays, if we're talking about 8 cross 8, right, those small systolic arrays tend to have low error probability at the same temperature, right? So that kind of imply, oh, if we want to care about the reliability, then we want to have design systolic arrays to be very small for those autonomous driving workloads, right? But is that the solution? There is a drawback. If we are going to have a very small systolic array, which would mean your throughput would be low, right? So you have the performance impact, okay? And also you can see here is that the detection itself have relatively large error rate, right, compared to other workloads. So detection is most sensitive at high temperatures. So that those observations actually motivate us to think about, is there a possible way we can do some kind of error mitigation so that actually going to introduce our DFA OPT, where we try to find the best systolic array size to map each layer, because you have a heterogeneity in terms of error rate across different systolic array size, across different layers, right? So can we use the large systolic array for more robust layers, which you don't require a lot of protection? Then we want to use large systolic array to give you high throughput. Here, the best, we mean both the accuracy and the throughput. So by using our DFA OPT, we were able to show that by doing this careful mapping, layer-wise mapping to identify the best server size for each layer of your workloads compared to the single systolic array size used uniformly for all the workloads. You can see our approach, DFA-OPT, can achieve a much higher accuracy, right? Both at grade 1 and grade 0. So here shows how does the DFA OPT select the different size systolic arrays, right? So if you look at it here, this is our DFA OPT. We were able to achieve similar to uniformly large systolic arrays performance, right? And here we were able to achieve the best accuracy as well. And here you can see the shaded area, gray area, tells you how much percentage of different size has been selected by the DFA OPT, right? So alternatively, you can use definitely 4x4, the smallest systolic array, which will give you the very high accuracy compared to other larger systolic arrays. But you can see here, the smaller systolic array yield to the largest computation cycles. So it sounds like we're gonna in order to achieve the robust autonomous driving workloads, we're gonna to have a mix of different size systolic arrays, right? Now the question is, if we're going to have multiple different systolic arrays, how do we integrate them into the SoC? We can do it monolithically, right? Like what we have been doing today. You have a larger SoC with hundreds of IP blocks, which are monolithically designed. Or we can also think about chiplets, which are a hot topic in recent years by leveraging 2.5D, 3D heterogeneous integration that can help us to integrate different smaller specialized designed chiplets into a larger chiplets-based system. So this this really motivates us to think about how do we efficiently design a chiplet system, right? Especially if we look at think back about our question, the gap between the AI algorithm developer versus AI hardware designer, right? So we want to answer the question is that, can we enable software developers also build their own AI processors, right? If we're talking about a chiplet-based system. If we look at today's AI development cycle, right? So you have the AI algorithm that's actually represented by a computation graph, okay? And then if we're talking about heterogeneous integration, chiplet-based system, you're gonna to have a very large design space, right? You have multiple tiles. For each tile, you have different compute data paths, you have different memories. And then the question is, how do we map this AI algorithm to the chiplet system? To do so, we have been working on a lot of this 2.5D, 3D simulation frameworks. One of the work is called HiSim, and we integrated this AI algorithm compute graph extraction, and then we do some compute clustering on the row graph. And then our HiSim library has a library of composable triplets, which are characterized across the silicon data that would tell you each triplets if you want to design the characteristics of them. And then actually in the last year's data, we have a paper talking about a library of the triplets that we can enable this closed loop analysis. So the question we want to further ask is, if we have a way to model the chiplet system, can we actually do some co-design across the chiplet algorithm, right? So the goal of the approach is to find the Pareto optimal solutions. And we want to look at both the accuracy and the inference latency and energy. So if you look at here, those blue lines are the baseline NARS, the neural architecture search approach, which do not look at any hardware triplet characteristics. They are only looking at the, let's say, the task inference, and then they find the best neural architecture that give you the high accuracy. Right? But if we're gonna to eventually run those AI algorithms on the triplet system, we want to enable this triplet algorithm co-design, which going to yield a larger design space. So in terms of the algorithm, we're going to search not only the model architectures, model weights, but now if we have the triplet system in the picture, we're going to also look at what is the best systolic size, right? Similar to our DFA drive, how many systolic rates, what the memory size, what kind of triplet library you want to have. So there is also a joint mapping between the algorithm to the hardware space. So we can do this everything through the brute force search, but it's very slow, and we want to find the automated optimization to achieve this Pareto frontier. That's come with our next work called triplet NARS, where we enable this triplet-aware neural network search for the 2.5D integration. So due to the time, I'm gonna just quickly go over this work. So essentially, we build a closed loop framework which going to explore the 2.5D triplet design space. So we adopt a NARS approach where we use the tree-based estimator for the sample efficient search. And then the underlying it is our Clara triplet modeling framework, which is a 2.5D triplet library for fast hardware performance modeling. And then we have a mapping module, which gonna to optimize the systolic layer-wise mapping when we do this cross-search across the model architecture versus the triplet architecture. And during our search trial, every trial we would receive the feedback from the inference latency energy to guide the next round of the optimization. So here are some simple way we can uniformly consider both the task metrics such as accuracy and the inference latency and energy cost on the triplet system. And you can define the candidate model architecture as you like, right? So in our paper, we have shown a use case for the conditional ResNet, but as a user, you can specify your own search base if you have interested deep learning model or large language model in mind, right? And this is the triplet library that we used to build on top of our triplet NAS, which is a systolic rate-based triplet library, where we have a lot of analytical models to characterize the power performance area for triplet level evaluation. Right? So those PPA numbers are calibrated at TSMC 28. And then here are some quick results that we were able to show in this ASP.DAC paper by looking at the ISO accuracy, right? So if we are looking at the SAM accuracy target by comparing our triplet NAS algorithm triplet co-design approach versus a baseline NAS, where you only perform NAS on the model side and then directly map to the triplet system, right? So you see here they achieve roughly the same accuracy. But in terms of latency, we were able to achieve 20% faster by doing triplet NAS. We can achieve up to 2x energy saving with more than 2x MAC operation reductions, and then we can also achieve up to 4x memory reduction, both at the same accuracy target. So here are more detailed information of the solution that found by the triplet NAS versus a baseline NAS in terms of the mapping solution, right? So you see here, triplet NAS was able to find more compact models that not only going to preserve the classification accuracy, but also because the model are more compact, so they would be able to deliver reductions in energy and latency. And here are some more detailed results on what exactly the layer, what the size of the layer, and what is the mapping space for our triplet NAS versus the baseline NAS. So you can see there the triplet NAS produce smaller layer size compared to a baseline NAS, right? So that's why those smaller layers would be able to map to smaller cytolic arrays so that we can reduce the hardware cost. So here are some detailed more information about when we do the search, the tree TPE based search, how different it is compared to a baseline NAS, which do not look at the triplet architecture search space. But when we do this core search, the solution that would be different across different trial numbers. So the key takeaways is that the triplet NAS is a closed loop, the NAS framework for joint optimization of AI model architectures and also layer-wise mapping to the 2.5D triplets. And we hope this this kind of work is serve as a starting point for the automatic synthesis of AI computing systems from the library of composable triplets. Yeah, so Bo, I think we are about the hour, so I would skip the last work,
Okay.
which I really hope to share, but yeah.
We don't have a very strict time limit. Yeah, I think
Okay, then maybe I can quickly
yeah,
go over
yeah, yeah,
in
yeah.
5 minutes. How about that? Yeah. Yeah, so now with this kind of the several works we discussed, let's come back to the first question that we asked. How do we close this gap, right? The gap between the IC hardware designer versus the software developer. Especially the question we want to ask is, how can we enable software developers to build their own AI processors, right? Chiplet NAS is kind of first step, but can we push it even further, especially in today's generative AI era, right? Can we leverage AI to help us to close this gap? So that's why we have another line of work which we have been looking at to leveraging AI to enable fast AI accelerator design. Right, the specific AI architecture we look at is CGRAs, and in recent years, our group has been working heavily on the CGRA, the whole tool chain from the compiler to the architecture generation to the VeriSci to the chip design. So we want to use the CGRA as a vehicle to look at if AI can be help here. So what is a CGRA? Essentially, CGRA is very similar to say solid array, but slightly different in terms of the flexibility. So CGRA is an array of interconnected computing units, right? So it's very similar to a 2D array of PE processing elements. The function of data flow can be programmed at runtime. That's the casing of the CGRA. So what's the benefits of CGRA? CGRA offer higher energy efficiency than CPUs, GPUs, and FPGAs, but more flexible than the ASICs because of the programmability, the reconfigurability at the runtime across the interconnected PEs. So is designing CGRA hard? The answer is yes. Why is hard? Because if we look at the CGRA design space, it's really span both the compiler side of the thing versus architecture selection, right? So what you say here at the software level, in order to enable the efficient mapping, you can explore a lot of those similar to HelloSense concept, the unrolling factor or the vectorization factor to optimize your source code, right? Similar to SMD kind of idea, right? So you can optimize your source code so that your computation graph can be better leveraged, let's say, parallelism on top of the 2D spatial arrays, right? So those are the compiler level optimization options. And at the architecture level, there are a lot of selection choices you need to do, right? You need to decide for each tile what kind of functionality you want to have. Do you want to do a full MAC operation, or do you only want to do a, let's say, simple addition or simple multiplication, right? And what's the size of your CGRA fabric would like, or what the memory capacity and also the interconnects, right? So it's really a large design space that make designing CGRA a hard question. And traditionally, state-of-art CGRA flow still have their challenge, although our group has been heavily investigating the automated design flow for CGRA efficient design. But when we look back on what we have done there are still a lot of challenges in our flow, right? So for example, there is a lot of heuristics that still inside the existing CGRA design flow. For example, how to design a low power CGRA for embedded domain. If I give you a FR, FFT kernel, right? So that would really need still expert to do a lot of iteration trials to converge to the best, let's say, the architectures. Second stage make this problem even harder is that the design space is really, really large, right? As I just mentioned, there are design parameters in hardware space. There are design parameters at the software space. So for example, even if we only iterate those candidate options, that would give us a total of more than 67K possible design points. How do we really quickly navigate or search through these different design points that would yield optimal CGRA design, right? The third challenge is that there are a lot of sequential decision making because the nature of CGRA design is quite sequence, right? You start with CGRA design generation first, you generate your fabric, then you're going to do the compiler mapping, right? Once you have a compiled design, you're going to go through the EDA flow, right? And then, assess your PPA, right? So this is also a long horizon decision making. Whenever we involve a large design with the commercial EDA flow, it's quite slow, right? And oftentimes, the mapping it depends on your workload kernel itself. Oftentimes, you would have fail during your mapping. Then you need to go back to your design to tweak other options. So this is already on our state-of-art CGI flow, but we still have these issues. And in recent years, we know that everybody, almost everyone in the hardware domain have been exploring the agentic flows, right? Especially people have been starting looking at, can we use generative AI, right, to help us to automate this space? And what we found is for at least CGRA design, single ARM agent will fall short, right? So why is that? Because single agent ARM has very limited CGRA specific knowledge. And especially for CGRA, as we just mentioned, it's really a long horizon task. And it has a lot of different stages, has a lot of sequential, require a lot of iterative refinements. So if we only have one single ARM agent, that it will over rely on the historical feedback. So what are the several issues when we start trying the single agent ARM based approach is that there are still a lot of frequent syntax mapping failures, and it's really the iteration is very expensive. We were not able to get a very high optimized design. So that's why our student has been looking at really a multi-agent ARM for frameworks for this complex design task. So here is a big framework picture, highlight the several case stages in our Markov framework. So the high-level philosophy is that we want to dedicate the different agents to handle each stage and then jointly complete the CGRA design. So you see here there are multiple stages being highlighted in our macro flow, and at each stage we have some dedicated agents to do the specific jobs. So for example, in stage one, we want to solve the problem that ARMs heavily rely on the historical designs during the iterative design process. And the way we deal with it currently is that we introduce a control knob that's gonna to steal the agent choice. It's kind of like a bandits like river learning approach where you have epsilon that control your trade-off between your exploration versus exploration when you are doing this search. And here are some prompts we developed to do this process. And then in stage two, we want to solve the problem that ARM generated CGI design often still have errors, right? So in order to do that, we introduce two repair libraries, basically controlled by our agents to identify and fix the errors. And then the third stage, we also say that the EDA2 evaluation is very slow, but if we directly ask RM to do prediction, it will do a bad job because all those commercial tools, they itself is an NP-hard problem. So the way we do that is we introduce the agent there, but we adaptively switch between the EDA tools and the ARM agent based on the confidence. If our ARM agent confidence is low, we're going to revert back to the full EDA evaluation. Only if our agent show high confidence in terms of the PPA prediction, then we're going to use the agents. So now let's look at some evaluations, right? So in terms of evaluation setup, we build the Marco on top of our open CGRA flow, which is open source CGRA design flow. Everybody can download it and try it. And we use ASP7 technology library to evaluate our design qualities. So here you can see several ablation studies, right? So if you look at our Marco versus another version without the exploration and the exploitation trade-offs, you see the Marco design can achieve the best speed-power trade-off. And also in terms of adaptive selection, that the confidence score introduced by RAM, right? We instead of blindly use RAM to predict the power performance area. Our design, we adaptively select between the EDA tools with our agents in stage 3. You see that our Marco was able to largely reduce the runtime compared to only using the EDA to do the evaluation. And in terms of the repair rate, right, let's say you have some compilation mapping failure, and then can we improve the pass rate? You see here, we can largely improve the pass rate by significant amount of the percentage rate by looking at different models. And if we compare the Marco with the faker or without a CGRA faker. And in terms of the design turnaround time, you see when we compare the Marco with the manually designed flow, which is the current state of art, if you want to design the CGRA manually, right, you can leverage this ASAP flow to do it on your own. But if you are using the Marco, that can achieve a large speed up to 5x faster than the manually designed CGRA. And here shows the along with the iterations, Marco improve the design quality when we are looking at later more optimized design iterations. And we also know this scaling law, right? If we have more data, if you have larger models, you have a high prediction accuracy. So we also evaluate Marco under a different scaled up larger ARM backbones, right? So clearly you can see there, right, under different application kernels, Marco can generalize well across different larger tested ARMs. So if you are able to you have access to bigger, stronger ARMs, and then you apply our Marco framework, you can get a better design quality in terms of CGRA design. So we also validated the Marco generated CGRA in terms of the layout, right? So we performed the whole physical design flow on top of the Marco generated design, and then we were able to generate the layout by using the ASP7 PDK. And here are some of the specs this design has. And here, what is showing there is for different approaches, what kind of a decision, what kind of architecture parameters are associated with the design. So we also integrate the Marco interface into the CGRA flow, which is our open source CGRA design flow, so that now if you use the CGRA flow, you can talk to the tool, specify your needs, right? Tell the tool what is your kernel, what do you want to do a high performance design or low power design. Then the Marco will take over the design space exploration and then generate the optimal CGI design. So traditionally, without this interface, you need to manually do all these selections based on the CGI flow. So here is a demo. If you guys are interested, feel free to scan and take a look. So that's all. Thank you so much, and I'm so sorry to running late in the talk.
Thank you, Jeff. So this is a very, very comprehensive talk and covering a lot of the very important stuff in the modern AI systems. And so first, any questions from the audience?
Oh, hi, Professor Zhang.
Hi. Yeah.
Thanks for your wonderful presentation. And actually, I have a small question about your simulation framework for autonomous driving. I remember it has been accepted. Oh, this one, DFA. Oh yeah. I noticed that your method so achieve both the accuracy and the low latency. And you also mentioned for the smallest, like systolic array, like 4 by 4, it can maintain the accuracy, but the latency is very, is higher than the larger systolic array. And so you flexibly switch the systolic array sizes. But how do you achieve the highest accuracy without losing the latency? Because in some cases you have to maybe switch back to the smaller systolic array and you still keep the low latency.
Yeah, so this is the coming from our observation, right? So
Mm.
our fault characterization shows that the error rate is very, very different across different layers. So some of the layer are more vulnerable, some of the layer are more robust. This is the first observation.
Oh,
Second
really?
observation is that for the same layer, if you mapped to a smaller systolic array versus you map to a larger systolic array, the error rates showing up, the delay faults showing up is also different,
Oh,
right? So smaller
oh,
systolic array have actually lower error rate. This is under the
oh,
same temperature condition,
mm,
right? Uh,
mm.
but a smaller systolic array going to give you lower throughput, right? So that's why you have a
Ah,
way to carefully
oh, yeah,
map the design instead of
yeah, yeah.
using one single systolic array size
Oh,
for all the
oh,
workloads. Right now, you have a way, depends on the sensitivity, depends on the error rate. Then you can clearly, carefully mapping it so that you can improve it. So the baseline is important. We are comparing with single size category system.
mm. Oh, I see. So you fully exploit those observations and so you can, this observation give you, your team the flexibility to achieve both the Pareto optimal solution.
Exactly. That's the main goal of this work, right? With this kind of
Oh,
framework, we
oh
hope
yeah.
we did similar to a case study. We show that you can use this framework to do full characterization, right? Either you can
Mm,
use do it with very detailed hardware
mm,
simulation, which is slow but most accurate. But you can also enable using our software-based emulator. But with this
mm.
framework, you can do the full space characterization that can uncover some of good observations, then you can leverage those observations to do design optimization, right? This is just one way that we currently find you can optimize it. But of course, there
Oh,
would be other opportunities if you do some other characterizations leveraging
oh.
this framework.
Oh, now I fully understand. Because of the platform, you can fully, explore those, get those observation, and because of those observation, you can achieve both the accuracy and the low latency.
Right,
Oh,
right.
yeah, yeah, perfect. Yeah. Actually, I remember at the last project you talked about the CGRA. So I have one maybe a rough idea. Can you use the CGRA for this one, for the flexible systolic arrays, because you can design one large systolic array, and you flexibly, reweld those connection between those PEs to make it adaptive.
Yeah, definitely. That's a great question, right? So
Yeah.
we can definitely explore instead of different fixed data
Mm,
flow accelerators, you can profile, let's say, a set of systolic rays, right? What
yeah.
kind of systolic rays you want to deploy here? When we think about the reliability,
Mm,
besides the latency, energy consumption, right?
yeah.
To leverage this, reuse this framework to work on other accelerator architectures. And
Mm,
also, you say the triplet system architecture is also a natural extension. If we're going to talk
yeah.
about the set of different systolic arrays
Yeah.
under the investigation. Yeah.
Oh, yeah. Thank you. Thank you. Yeah.
Thanks very much. Good question. Yeah, I'm
Thank you.
happy.
Some other questions from the audience? Actually, I have several questions, but since we already become running a bit late, so I just want to ask one questions. So Jeff, also for your last work on those the multi-agent CGI, uh, I'm not quite sure that. So here this is mainly for the front end, right?
So you mean front end design?
Yeah.
Yeah, yeah,
This
yeah.
those the agent is mainly for the front end design.
Yeah, so we are looking at the software mapping space and then hardware generation space. We are not looking at the physical design part
Okay.
but definitely we can extend, right? There are a lot of good research nowadays looking at, oh, can we design an agentic flow for, let's say, open road physical design flow, right? But those can naturally, connect together, right? Because when we generated our design, we did use the menu, open road flow to generate
Mhm.
the layout, but we didn't fully optimize it
Okay.
with the agentic flow. Yeah.
So my question is that for this front end is also includes the RTL development or not?
Yes. So the output, the final output of our Marco is the
Mm.
mapping and then RTL of CGRA.
So it includes the RTL. So I was wondering, so like for the verification part for those RTL, so you also use the agent to do that, or using some kind of existing commercial tool?
Yeah, so currently for the verification, we used the commercial tools. We didn't develop a separate set of flow, RM-based flow to do the verification. But yeah, definitely that's a separate topic. A lot of right nowadays people are using RM to do everything, verification, design,
Yeah.
software
Yeah.
mapping, physical design. Yeah, yeah.
Yeah,
But we haven't. Yeah.
because some of my rough thought is because for CGI or for other like AI style, like those the design, so it is kind of the inherently quite a kind of the structure, the regular. So in that case, actually, I think that so the verification challenge for this kind of the regular design may be much lower than when you
Mhm.
want to do the verification for those kind of general purpose design. Yeah. So yeah. So that's
Exactly.
just on my thoughts. Yeah.
Yeah, yeah, that's also the reason we want to first look at the design challenge first. We want to solve this problem, right? And
Mm.
then the verification, that can be an add-on, but it's also very, very important for close the hardware
Okay.
development cycle. Yeah.
Okay, thank you. Thank you so
Thanks.
much. So thank you for spending such wonderful time to give us this very good talk and thank you so much. And also thank everyone to attend our this week Efficient Seminar talk and next week will be our last talk this semester. Okay, so see you next Tuesday. Next Tuesday our talk will be a little bit later, will be 11:15 instead of the 11. Okay. Thank you everyone. Thank you, Jeff, again. Thank you.
Yeah. Thank you, everyone. Thanks for your time.
Thank
Bye.
you. Bye.
Have a good day.